Welcome to Hashtag Trending, the Weekend Edition. I'm your host, Jim Love. We've heard a lot about quantum computing these days. Somehow it seems to me, though, it's more like nuclear fusion. And the reason I say that is we all have all these great advances. They make the news, you read a story, but the actual idea of using it in business somehow always seems a long way off. And for me, it seems I understand quantum computing conceptually. What I struggle with is why it's possible. And I've never had this problem before with what we call classical computing now. It sounds like classic rock, classical computing, but maybe, though, it's because I grew up being able to see transistors and how they work. And even though we talked about putting thousands and possibly millions of transistors on a silicon chip, and that's a feat of engineering bordering on magic, I still know how it works. But quantum, it seems more like actual magic. Things that exist as probabilities that could be linked over potentially vast distances, things that exist as probabilities and can be linked over potentially vast distances and affect each other even without a known connection. The things that only truly exist in a state of uncertainty till you observe them. And the only comfort I can take from all this is that even Einstein struggled with this, and I'm not in his league by any stretch. He called entanglement, part of quantum mechanics, a spooky action at a distance. And so we're left with this question: how does it work? Why does it work? You hear about it, and it just doesn't seem real somehow. It still seems like a lab experiment. And I go back to that nuclear fusion parallel. Great idea. You can sustain it in a big lab in CERN somewhere for a few seconds, but that's it. But lately, there are signs that quantum might be more real than we think. We've all heard of, at least if you're a follower of the podcast, you've heard about the quantum processors that IBM is placing in universities. They just announced one major U.S. university will get an IBM quantum computer, and they're going to start to donate quantum computers to several other universities in the U.S. And with that, suddenly it seems a lot more real. And as always, I've been interested in what's happening in the big world. And it turns out there's some work being done in Canada, advancing the idea of quantum computing in commercial usage. And recently I ran across a group called the Quantum Algorithms Institute. It's a collaboration between government, academic community, it's a collaboration between the government, the academic community, and Canada's growing sector of quantum computing companies. And they work with companies across all industries to build experience in real-world application of quantum solutions. My guest today might make it even more real. She's with a program that's preparing people for careers in quantum computing. She's a professor at Wilfrid Laurier University and the Chief Technology Officer of the Quantum Algorithms Institute. My guest today is Dr. Sohini Ghosh. Welcome, Dr. Ghosh.
Thank you so much for having me.
It's been fantastic, and I just can't wait to talk to you about this. But I have to tell you, this has been a difficult interview to figure out. I want to introduce you. I want to talk about quantum computing in general so that everybody knows what we're talking about. Then I want to start and get into this careers training program and making this a reality. And I was struggling with where to start. And since I'm not a quantum particle, I can't occupy 3 states at the same time. So we have to tackle one at a time. So let's start with you. Tell me about your career and what brought you to where you are today.
That's a great question to start with. I am certainly perhaps a real life example of, I don't know if it's quantum uncertainty at work, but certainly uncertainty in the sense that I don't know if I have ever expected to follow the career that I did. So I was born and raised in India. I was always a very curious little kid. I think like a lot of kids out there. And I also dreamed of going out to space and exploring new worlds and things like this. So that dream eventually got converted into not necessarily exploring new worlds out there, but exploring mysterious questions right here on Earth. And the most mysterious of them all is, of course, how do the fundamental laws of the universe really work? And that's what led me into physics and eventually into this field of quantum computing, which was not actually a thing when I was a graduate student starting out. I was just exploring foundational questions in quantum physics. But by now, over the last couple of decades, it has become more of an applications focused area, this whole area of quantum computing, quantum information security. So it's been exciting to see that change and be part of it.
So that explains a little bit about it, because there are lots of technology directions you could have chosen. Quantum computing it's a different one, but you started out from quantum physics and then moved towards the quantum computing area.
That's right?
Correct?
Exactly.
Okay. And you're a professor at Laurier as a former Waterloo prof. I won't hold that against you. I'm just kidding. And everybody knows the joke between Laurier. They're
yes,
cooperative groups of people in the world, but there's always that friendly rivalry. But this project you're on is in BC. Now, you don't manage this by quantum entanglement, I'm sure, but how do you manage those two things?
Actually, I do joke occasionally. I wish we can build something like a quantum teleportation device. So quantum teleportation is real, but unfortunately it doesn't teleport human beings or even matter. I'm sure we'll get into that in a little bit. But yes, my role is actually divided between BC and Waterloo. I still have my faculty role at Laurier, but at the Quantum Algorithms Institute, I'm involved in various programs to try to take this whole field, which has been very theoretical and research focused, into a more applied direction and connect all this wonderful research and knowledge we have to industry, eventually, hopefully, to bring growth and economic development in BC and also in Canada. So all the Quantum Algorithms Institute is based in BC. Of course, quantum itself is not really about being regional. It is about all of Canada participating in this ecosystem eventually. So we're part of multiple hubs in the country.
As someone who lives in the center of the universe or close to it, it's nice to see some developments happening outside in other areas of Canada as well. And I think we know it's not a zero-sum game. We all gain if we make advancements in any of the tech sectors. Now, for anybody who didn't get the entanglement joke, and I would forgive them if they didn't, you got to be I'm sorry, I'm going to be a bit of a nerd, but I think you'll take that in a nice way that this is a specialist area. But could you, for the average person, give a definition of quantum computing and what that really means?
Sure. And I embrace my nerdiness, and I love to talk about nerdy things like quantum computing, which is in fact absolutely something that's not that easy to explain. As you said, when you have regular computers, it's, we all have experience with our laptops, and we can imagine what's happening inside a laptop where you have these amazing tiny little chips which keep getting more and more miniaturized, and you hear about all these next generation chips every single year and all of them, really what they are is basically they're switches which turn on and off. And that's what represents informations that are 0 or 1. It's on and off, very binary, simple. So I think we got pretty lucky that we live in a universe where we can build a computational framework based on just zeros and ones. And it's completely universal. That to me already seems amazing and quite convenient. So why do we need even quantum computing? Quantum computing is a little bit different because the idea is, why should we just limit ourselves to a binary approach of zeros and ones? The answer there is that it's because it works. It's easy and it works. And in fact, it works amazingly well for almost everything. But there are problems out there that are possible to do on computers, and the more powerful the computers are, the faster they can be solved. But some problems are so challenging that even our best computers have a very difficult time. It's just a matter of the scale of the problem itself. So it would be wonderful if we could figure out a way to make those problems tractable. And that happens if we can build more and more transistors and ever more powerful supercomputers. But what if we talk about supercomputers that would be the size of a planet? That seems a little crazy. So quantum computing is where things can get much better in efficiency, because we can use certain extra knobs such as entanglement and superposition to actually build computers in a completely different way and move away from just binary computing. And by doing that, expanding our framework for computing itself, by using these new knobs, we can actually make some of these extra hard problems really much faster. And that's what quantum computing is all about.
Great. I'm still struggling with this, and you gave a great explanation. But is it that quantum gives more power? Are we looking for a bigger computing solution, or is it just so different that it can tackle a problem in a different way?
It's both. So if you can take an existing problem and solve it faster, that's what we mean by computing power. To solve it faster, doesn't just mean crunching it with faster speeds, but as you said, taking a whole different path to the solution, which might be shorter. So maybe one way to visualize this is to think of maybe getting from point A to point B, and as you're traveling, you find, there's a giant mountain in your way. Now you could climb all the way over the mountain, which is probably what you would need to do, and that takes a lot of resources and energy and time. But what if you could quickly just walk through the mountain because you found a tunnel to get through it? That's faster. So you're still doing the same problem, but you're doing it faster, not just because you're somehow able to run very fast up and down the mountain, but because you've actually found an entirely different path. So quantum computing offers that as the speed up.
And can you give us an idea of the orders of magnitude in terms of the problems? Is there an illustration of a problem that could be solved by quantum that couldn't be solved by a regular computing, or within any sort of reasonable amount of time?
Yes, actually, the reason that this whole field was kick-started was because there was one very important math problem, which maybe you might not think of as very interesting, but it is very important, and that's factoring of a large number. So if I ask you to factor something like 21, sure, you can say 7 times 3. But if you go to something that has 200 digits, a big number, turns out that is really difficult even on supercomputers to solve that kind of problem. So we know that factoring is a hard problem. Why is that important? It turns out that it's the basis that we use for all of our encryption standards. The idea being that if a hacker wants to hack into our passwords, they would actually have to factor a very large number. And because it's very hard to do computationally, our passwords are hopefully safe. So that's an example of a problem which even supercomputers have a hard time to crack. But a reasonable size quantum computer would be able to crack that problem, we know, in a matter of minutes. So we're talking about significant power here.
You're saying that those types of calculations would now be available to us.
Yeah, so not every problem has a quantum solution that is faster, but some very important problems such as factoring, as well as another problem which we all basically know is important because we do it every day, and that's searching through large unsorted databases. That's what we call Google. So quantum versions of Google could provide significant speed up as well.
I have to ask about AI, sorry, and I was going to jump to this later, but while we're on this topic, the whole question of getting to artificial general intelligence seems to be one of computer power more than any idea of us not knowing how to put models together. At least that's a general theory. We won't know till we get there. But does the promise of quantum computing promise an advance in AI?
Well, I think AI is a complicated field because certainly we're building these models such as ChatGPT, which seem to be now at a point where they are at least pretty helpful in terms of being able to communicate in ways which seem like almost like they are mimicking some level of human behavior. But it's not clear to me that we're even testing for what we mean by intelligence. I don't know if we have even a definition of intelligence. That being said, we can think about what something like ChatGPT does and look behind the scenes as to what is it actually doing. It turns out it's doing a lot of mathematical calculations, including pattern recognitions, and a whole class of calculations which we call linear algebra based kinds of calculations. Machine learning is largely just that. And turns out those sets of calculations are exactly what quantum computers might be very good at once we build them. Now, they have to be large-scale quantum computers, so we're not there yet. But when we do build them, then, of course, that aspect of machine learning will become something where we can use quantum computers to make it more efficient.
Wow. Let me go back to where I started this. There's a lot of potential. I think there are some huge jumps that could be made in terms of computing if we could use quantum computers. But are we really close to having a real functioning quantum computer that can be used in general usage? And I don't mean, on my desktop or anything, but where we could use it without it having to be us to say we just don't have quite enough there yet.
I'll answer that question in two parts. Firstly, I want to say that we actually have had an existing quantum, not a full universal quantum computer, but a quantum processor developed in BC actually for quite a while now. And that's been developed by a company called D-Wave. It was the first company in the world to offer any kind of quantum computing for commercial purposes. And in fact, over the last couple of decades, they have actually worked with various companies and have provided quantum computing solutions for a variety of problems in the real world, actually. And they have been able to demonstrate performance improvements in certain cases. So that's already been done. Now, for universal quantum computing, we're not there yet. So there are companies, of course, like IBM and Google and many others now in a race to be the first to build that large-scale, robust quantum computer that can hack into everybody's passwords in minutes. Are we close to that? Not yet. I'd say but we're getting closer all the time because there's all these technical developments happening all the time. So in a few years, yes.
I did a story, I think, last year on this company on the West Coast. What was their name again? It was
D-Wave.
Yeah, D-Wave. But how does a company on the West Coast beat all of these other big computer companies to getting a commercially viable quantum computer?
Sometimes it just takes somebody to take that first leap long before anybody was really thinking about it commercially, long before IBM and Google came on the scene. D-Wave said, well, why not? Let's startup mentality. The other thing that makes them different, and the reason they've been able to establish themselves, is because they focused on a particular approach to quantum computing called annealing, which is not the approach that is more widely used by Google and IBM and everybody else. So annealing is an interesting approach because on one hand, there are certain types of problems that are better on an annealer, such as optimization problems. And those problems, of course, can also be done with other approaches. But because D-Wave focused on the annealing approach, they were able to build a processor. That's why I called it really a processor rather than just a universal quantum computer. They were able to build a device that essentially specializes in optimization problems. And that allowed them to focus and scale that aspect up to the point where it can be used for certain types of real-world problems that are best suited for that kind of annealing approach.
For the general amateur like myself, can you give an idea of what that approach is and why it's different? I'm fascinated. So what is the difference with their approach?
So do you want me to get into the optimization?
I'm fascinated.
Okay, so maybe I'll step back and say that the sort of standard approach to quantum computing is what we call the gate-based or circuit-based approach. And what that means is it's like taking what we normally do with our regular computers and adapting it to a quantum approach, which means if you look at how people program a regular computer, essentially you give it a set of instructions to say, take all these zeros and ones, which is the information, and then combine them using all these different approaches, which in computer science language are called these gate operations. And that is eventually converted into circuits inside your computer. And the whole thing is executed step by step through the program that you've written. And it's a sequence of gates or a sequence that you write as a circuit. So the circuit-based quantum approach is similar, where you say, okay, here, take all this information, which is not just zeros and ones, but these are quantum information encodings, including all the probabilities and uncertainties, and then apply a sequence of instructions, which are gates. And these are quantum gate operations. And so you build an entire circuit of these quantum gates, which we call a quantum circuit. And going through that entire sequence will give you the solution. So that's what's called standard. And it's pretty intuitive in the sense that it's basically the same as regular computers, just using quantum gates and quantum operations. D-Wave's approach is very different. This is not a gate-based or circuit-based operation. The idea is, if you want to find the minimum of a function, what you do is you encode that problem into a quantum problem such that the minimum energy of that problem is the solution to your problem. So I know that sounds wild, But maybe a picture you could have in your mind is that it's a search through a landscape, which is your function. So there's some mathematical landscape that you have to explore to get to the solution of your problem. And if you think of it actually like a landscape, there are hills and valleys, and one of those valleys is the minimum. And that's the minimum energy of the entire landscape. So if you could maybe flood that landscape with water, you would want it all pool into the minimum. So really, a quantum annealing approach is like using a quantum wave that will eventually flow to that minimum point. And that's how you do mathematics, which is wild, isn't it?
Isn't it amazing that sometimes we find the solution to huge technical problems just by looking at them a different way?
Absolutely.
It's just magic sometimes.
To me, that is the most fascinating way that we can move forward. It's creativity, right? How do you take something that nobody else has ever thought about it in that particular way and unlock something new?
Yeah, which is one of the things that I really most troubles me, is that I don't think we are teaching mathematics and computer science in its magical sense and in its interesting sense in our schools these days. I hear a lot of call for coding and a lot of that, but there's so much magic in problem solving. And when you talk to mathematicians or physicists, it really is an imaginative world.
You're absolutely right. I feel like those of us who choose this field or anything math and quantitative, it's almost like the ones who got into some kind of secret society where we all know that it's so much fun and exciting and nobody else sees it. It's a little bit strange. You're right.
Yeah, but great. I'm going to ask you one more quantum question, and just because I've got you here at that, you can charge me, and I'll take your course next year. But the one thing that always amazes me when we talk about quantum computing is the one thing that I know about quantum effects is that when you observe them, they lose their effect. In other words, superposition, yes, I think is called, disappears. How do you gather information from a quantum computer?
Very good question. And this also leads to this related idea that, you often hear or in articles about quantum computing saying how a quantum computer explores all solutions at the same time. So then you wonder, wait, if that's true, then how do you get to the answer? Because the problem is when you measure, you don't get all the solutions observed. You can only observe one of all of the possible solutions. So how do you observe the right solution? So getting information out of a quantum computer through observation always gives you what we call classical information, meaning just one solution that's not in superposition. There's no entanglement anymore. It's just become just another regular message like what on your regular computer. So the goal always is to try to create a quantum algorithm, which is just a sequence of instructions or a recipe, to search through all of that quantum space of what potential solutions in a clever way using superposition. But in the end, when you observe, you're going to observe one of the possible solutions, which is just classical information. You want to make sure that the probability of that final observation giving you the correct answer is maximized. So you have to force the calculation to increase the probability of the right answer. But in the end, you always project into a classical sequence of zeros and ones, actually. I don't know if that answered your question.
Oh, no, you're explaining this with marvelous clarity. I
my
wish
gosh.
I'd met you a long time ago because I've been reading about this and trying to understand it, and I think we all are. And I think because we conceptually want to understand that before we take it to the next level, which is how do we use it in real life? You have this program, and it's to prepare students for careers using this new type of computing, quantum computing. I'm presuming that's largely as programmers. Is that a wrong assumption?
Not necessarily. So when you say that we have a program, Quantum Algorithms Institute itself is developing certain types of educational materials that are designed to be upskilling people who have an interest in this field and just want to learn a little bit more about it. Now, keep in mind that building an entire industry and ecosystem means it's not just about having programmers. Even with regular computers, imagine if you just separate out all the programmers and say, yeah, you're in charge of everything. That wouldn't really work. There's A lot.
Programmers would like it, but it's probably not a good idea.
Exactly. So programming quantum computers is one aspect, but there's all kinds of other careers that need to be developed, such as just generally sales and engineering and communications. All of the different aspects of quantum industry are important. So what we do is try to make pathways clearer for new students or even those who are already, let's say, programmers or engineers who have already a career and are looking to expand or shift gears. We provide ways for them to do that.
I think that's wise advice, that there are many other aspects of how you could pursue a career in this. But let's just isolate quantum programming out for a second and talk about that. Why is it different from regular programming? I think we've talked a little bit about this in terms of having different approaches, but they have different there are different languages, there are different things I'm going to learn. What would that be?
Yes. Quantum programming is absolutely about being able to tell a quantum computer to do the calculation, as I said, using this different approach. So instead of climbing all the way over a mountain, you have to tell the quantum computer, please find the best tunnel through the mountain, right? So if you were just thinking of this in terms of just different languages, it's saying, I already have a way to tell the person to climb over the mountain. I don't have a way to tell them to tunnel because that was not something that was built into my previous set of instructions. There was no instruction which says, please tunnel through. So now we have new programming languages where an instruction such as please tunnel through would also exist. Now, obviously, this is just an example with the mountain. In the context of quantum computing, really the extra instructions we need are essentially telling the computer to say, build this kind of superposition or use entanglement in this way. Those are the kinds of extra instructions that we would need a quantum programmer to know how to do. So that's why quantum programming is essentially like a broader language than current classical programming. Classical programming is a subset of what we now know of as quantum programming.
When I started out, there were people who programmed an assembler very close to machine language, and they were very in tune with how the machine worked and at a very basic level. And then we got COBOL and business language type programming. Will the quantum world eventually break down into those two elements as well?
I think you're absolutely right. So if one tried to predict what's happening now is we're not going to discard everything we already know about programming for our classical computers. So for example, currently, if you wanted to go on IBM's quantum website and start programming their quantum computer, which you can get an account and try it out for yourself. There's a free account for now. So get it while you still can before they lock that down. But if you go on there, there are different sort of platforms depending on your skill set in programming. So if you just want to play around, there's even a very visual tool you can use where you can basically just drag and drop these quantum gates and build a circuit. But if you are, for example, familiar with programming in general, so if let's say Python, you can use Python to actually program the quantum computer because that you can write Python code which tells the quantum computer, okay, build this superposition and this entanglement. So that's, I think, what's going to happen more and more. We're just going to get layers of programming.
You're just encouraging those Python programmers that they can do everything now. You know that.
I hope they will first get the training that we're offering at QAI, and then they can go away and do anything they want.
Absolutely. So how long do you think it's going to be before people will actually start working day to day with quantum computers in general industry? And I know it, maybe not at the smaller businesses, but maybe how many years do you think that is before we actually see a more common usage?
Well, that's the kind of question that's always the hardest to predict, right? Whether that's quantum or AI. Just if you think back with AI and predicting how ChatGPT would suddenly overnight change the entire conversation of what we consider using machine learning for, I think that was unpredictable, although actually machine learning was being used in many industries before that. But that sudden change and in a peak was hard to expect. Quantum might be the same. where over time we'll see slowly different, very specific boutique applications first being developed, which we wouldn't be aware of in the general sort of setting. But at some point, perhaps there will be some big sudden change where there'll be this obvious way that everybody can engage. Not sure what that will be, but the slow rollout of the technology, it's already happening. And as I said, within the next 5 to 10 years, I think we expect there to be some significant kinds of impact of this technology in various sectors.
So you're saying people should start experimenting with it now, learning with it now. And I totally agree with you. How does technology change? Slowly at first and then very quickly.
Yes,
So
exactly.
you never know exactly. So what are the things, if like I say, I'm a pretty good programmer, or well, I'm not, but guys like me are average, let's say competent. If we're interested in this, do you have to be at a genius level to really have a viable career in quantum programming?
Absolutely not. I think another thing about the sector, which also applied, of course, back when regular computers were first being developed, as you said, the programming languages that existed were very basic. Literally, they were called basic, right? The idea being that anybody could actually start writing because there was nothing out there, right? The reason we now have these very specialized coders is because the code itself has become very complex, right? We are talking about millions of lines of code and layers that no one person could actually know everything about. That doesn't actually exist in quantum as yet. So if you come in now, I think it's actually the point where it's the easiest to get into the programming field, because you get to build those foundations without having to learn everything that's already happened, without having to read millions of lines of quantum code that somebody else has written. So I don't think it is about being really an expert or a genius. It's about playing around with what exists now and building. Anything you build is going to be new and fresh. So everybody has an opportunity to contribute. I think of it more back when Apple introduced the App Store. And there were people who could have predicted that Angry Birds would be something, right? You don't need to be a genius to write about how to develop a game like Angry Birds. Or maybe you do, who knows? But my point being that anything can be the next big thing in quantum.
So how should people start exploring this? You said you don't have an actual program. You're making materials available. How should people engage? I think you've first said IBM has a processor that you can actually get on and explore with, and they've advertised that before. What are other things should people be doing, and how should they be engaging with this?
I think the first stop could be for people to check out our website at Quantum Algorithm Institute, which is exactly about building those kinds of bridges, depending on what level you're at. If you're maybe a beginning student, or maybe you're already in the industry, there are different ways to engage. And that's what we break down. We have launched this new website called the Careers website in Quantum. And that basically gives you an insider's look into various different companies who have partnered with us on this website. So they can tell you a little bit more about what the different companies are doing. But broadly speaking, you could either take a very academic route into this field. So if you're a student, there's various university programs, all the way from bachelor's through to master's to PhD levels that you can take. You don't have to actually have a PhD in quantum to be able to be part of this industry. But if that's something you want to do, for sure, you can certainly do that. Beyond that, there are many other ways. Yes, you can go on IBM Quantum's website and start playing and learning on your own. Or you can actually sign up for some of the access that we provide through QAI. You can do what we call a quantum boot camp. If you already have some coding knowledge, you can actually take this quantum boot camp course and upskill yourself so that you can learn how to code quantum computers. We have access that we provide to D-Wave system as well as other such platforms. So there are many different ways to start trying your hand out at these different platforms and learning some more. So check out the website, go explore on IBM, explore on D-Wave, whatever level of comfort you have is what should be guiding you.
And we'll, if I get those links from you, I'll make sure I put them in the show notes to go out with the podcast so that people can actually find them. And I provide instructions for people to be able to get those things. So that'd be great.
Great.
One more question I just want to ask you. You obviously invested a major portion of your life in this. You're passionate about this. And I know you can't predict the future, but what is the future you envision? What's your dream of how this will roll out in Canada and around the world?
I'm particularly excited about what we can build in Canada because honestly, we've played a huge role already in this field. For example, as I said, we had the first quantum hardware company here, but even before that, researchers in Canada were the ones who developed the first quantum encryption standards that are now people are creating these kinds of quantum encryption key distribution networks around the world. So we've already shaped this area, and we can do a lot more because we have the expertise. And what excites me is as we build our quantum ecosystem here in Canada, what can we do that would be a shining example to the world? For example, how can we make sure that as we build the technology and roll it out, that we give access in a way that is equitable and fair, and we create applications that are for the public good, such as in healthcare and in the energy sector, of course, and climate change. How do we address some of the biggest global challenges? I think I'm excited about developing a strategy that will be able to address these questions using quantum. And we already have a national quantum strategy. I'm very excited to be part of that council that advises the government on that. And because we're taking this measured national strategic approach, I'm very excited to see where we go.
And what should the average person be doing to support this? This is the future of our country. In a digital world, having these talents and having these skills and businesses built on them is the essence of our future prosperity. What should the average person be thinking about in ways that could help develop this?
Look, all of us live in this age of information. Everything that we do is about transmitting information, creating information, sharing information. That is what our life is all about. So information processing is the central aspect of our lives these days, which means all of us should have a voice in it, and we use it every day. We use the internet every day. We use computers every day. So I think that if we wanted to build something together where all of us are accessing and using this technology, we should engage with it at some level. So of course, not everybody needs to be an expert in quantum, but we all should be aware of where this technology is going, what are the possibilities and the potential for it, but also what could be challenges and inadvertent consequences if we don't, all of us, understand where we're going and use our voice. We all have a voice in Canada. We can use it through our local networks, our communities, or through our representatives. So I think I would encourage everybody to start learning a little bit about this. It's interesting. It's exciting. And maybe think about how you can either contribute to the ecosystem or just know about it and be able to voice your opinion about it.
This has been fascinating. Thank you so much.
Wonderful. I'm always very excited to talk about this, as you can tell. And thank you for giving me this chance.
Yeah. My guest today has been Dr. Shohini Ghosh. She's a professor at Wilfrid Laurier University and the Chief Technology Officer of the Quantum Algorithms Institute. And if you want more information on the Institute, I'll post links with the show notes at our new home at technewsday.com or .ca, whatever you prefer. Or write to me at therealjimlove@gmail.com or our new editorial address, which is editorial@technewsday.ca. Hashtag Trending goes there 5 days a week with a daily tech news podcast. And we have this special show on the weekend featuring an interview with experts and interesting people. Thanks for spending part of your weekend with us. We'll be back with the news on Monday morning.